Welcome to this explainer. Today, we're diving straight into the fundamental building blocks of motion, specifically 1D kinematics and dynamics. Whether you're just brushing up on these ninth grade physics concepts or you're genuinely curious about the invisible rules governing our physical world, we're going to break down the science of movement so it makes total sense. Let's get right into it. Here's a quick look at our roadmap for today. We're covering distance versus displacement, speed and velocity, understanding acceleration, decoding motion graphs, and finally, Newton's laws of motion. So, starting off with our first section, distance versus displacement and the absolute basics of movement. The absolute most crucial starting point in physics is understanding this stark contrast between scalar and vector quantities. It's a real game changer. Scalar quantities, like time or mass, well, they only care about how much, just the magnitude. But vector quantities, they care about how much and in what direction. Truly, keeping that distinction in mind is the secret sauce for accurately analyzing how things move. To really visualize this difference, think about the actual path you take to get somewhere. Distance is that winding, messy path you actually traveled. It's a scalar, meaning it just endlessly adds up the ground you cover, regardless of which way you're facing. But displacement? That's a vector. It's literally just the shortest straight-line distance from your start straight to your finish, pointing directly from point A to point B. Let's actually put this into practice with a quick example. Imagine a guy named John. He drives 250 miles north, realizes he forgot his wallet, and has to backtrack 105 miles south. Now his distance, the total ground he physically covered, is a hefty 355 miles. But his displacement? Remember, that only cares about his final position compared to where he started. So 250 miles north minus the 105 miles south means his displacement is just 145 miles north. And get this, if he drove all the way back to his exact starting driveway, his distance would be a massive 500 miles. But his displacement? A flat zero. Okay, moving right along to section 2, speed and velocity, where we start adding time into the mix. Just like distance is the scalar version of how far you went, speed is simply the scalar version of how fast you're going. It's just the distance covered divided by the time it took to cover it. And, exactly like distance, it's a scalar quantity. That means there's absolutely no specific direction attached to it. But as you know, speed usually isn't constant. Think about a standard road trip. If you cover 60 kilometers in 1 hour, that calculation gives you an average speed of 60 kilometers per hour for the whole journey. But that speedometer right there on your dashboard, that is giving you your instantaneous speed at that exact precise second, which is pretty much constantly changing as you drive, right? Now, let's contrast that with velocity, which is basically the vector twin to speed. Velocity is displacement over time, which means, you guessed it, it requires a direction. For example, if someone takes an hour to travel 10 kilometers to school, their average velocity is 10 kilometers per hour in that direction. But what if they're just sitting on a bench waiting for a train? Their position isn't changing at all. So right at that specific moment, their instantaneous velocity is a flat zero. Which brings us to section 3, understanding acceleration, or what happens when velocity changes. Acceleration is a vector quantity that tells us the exact rate at which speed or direction changes. It's actually pretty easy to calculate. You just take the final velocity, subtract the initial velocity, and divide that change by the time it took. So, think about it. If you speed up, if you slow down, or honestly, even if you just turn a corner while keeping the exact same speed, your velocity is changing, and that means you are accelerating. All right, let's switch gears a bit for section 4, decoding motion graphs and visualizing all this data. Let's start with distance time graphs. Time is always steadily ticking away on the bottom axis, and the distance traveled is on the vertical axis. When you see a perfectly straight, diagonal line pointing upwards, that proves the object is moving at a constant, unvarying speed. It's covering the exact same amount of distance in every equal little tick of time. When you compare different lines, you can actually read the speed visually. Basically, the steeper the line, the faster the motion. A much steeper line directly translates to a larger distance moved in that exact same amount of time. It's a brilliant, quick way to instantly see which object is moving faster without having to do a single math calculation. But you definitely have to watch out for this one. When the line on a distance time graph isn't straight and instead curves upwards smoothly like a ramp, getting steeper and steeper as time goes on, it visually proves that the object is accelerating. The amount of distance it's covering every single second is literally growing larger and larger. A single complex graph can actually tell the entire story of a journey. You might see straight diagonal lines showing steady speeds, or maybe a completely flat horizontal line right in the middle. That flat line means time is passing, but the distance isn't changing at all, so the object is perfectly stationary. Then you might see an upward curve, showing the object getting faster, or even a downward slope, which tells us the object is actually heading back to its starting point. Now, speed time graphs look incredibly similar at first glance, but pay attention here because the rules change completely. On these, speed is on the vertical axis. So an upward slope, that means speed is increasing, which is acceleration. A horizontal flat line doesn't mean it's stopped anymore, it means it's cruising at a constant, steady speed. And a downward slope means it's slowing down or decelerating. Seriously, always check those axis labels. And finally, we arrive at section 5, Newton's laws of motion, where we uncover exactly why all this motion happens in the first place. Sir Isaac Newton perfectly captured the concept of inertia in his first law. Honestly, I like to think of it as the ultimate rule of cosmic laziness. Everything in the universe is just going to keep doing exactly what it's already doing, whether that's sitting perfectly still or zooming through the vacuum of space in a straight line, unless an external net force violently interrupts it and forces it to change its state. Building off that, we get Newton's second law, which ultimately boils down to one incredibly elegant, simple equation. Force equals mass times acceleration, or F equals ma. It simply means that the heavier an object is, or the faster you want to forcefully change its velocity, the more physical force you are absolutely going to have to apply to it. Makes perfect sense, right? So, the crucial takeaway here is that by stacking these building blocks, we get the complete picture. We separate the messy path of distance from the straight arrow of displacement. We layer in time to get speed and velocity. We measure those changes with acceleration, track the whole thing on visual graphs, and finally apply Newton's forces to explain the why. By mastering these concepts, you can literally decode the movement of anything in the universe. As we wrap up this explainer, I want you to do me a favor. Just look around you for a second. Even if you think you are sitting perfectly still right now, you are literally on a giant rock spinning through space at 1,000 miles per hour. So, what specific invisible forces are maintaining your current state of inertia right at this very moment? Are you balanced, or are you actually accelerating? The physics of motion is happening all around you constantly. Thanks so much for joining me today, and as always, keep asking questions.